Hello everyone. So today we will discuss classification algorithms. So today we have in our agenda the discussion on these three algorithms. These are k nearest neighbors classifier, naive Bayes classifier, and decision tree classifier. So I hope that you have understood the purpose of classification. We are talking about a problem where we have the label data for training, and we are expecting our machine to be able to respond to the given set of training feature vector, and it has to predict the label. So it is the labeled class and the associated data for which we are preparing a classifier. So you've understood that we are talking about the training instances which are described by their corresponding features. The features are placed in the feature vector, and then they have the corresponding label representing the class. So training instances are stored, but no generalization is done before an instance for testing data when it arrives. So here you will see that k nearest neighbor is actually not training itself. It is not training any classifier, while whenever there is a testing required, it takes into account all data items which are there, all data instances which are there, and tries to check the proximity of the test data to one of those training data sets, and then correspondingly tries to associate the label for this test data. So here no hypothesis using training input and output pair is constructed. There is no hypothesis constructed, there is no error surface constructed, there is no parameter tuning required. We do not have any requirement of obtaining some kinds of weights. Here the new instance is examined with respect to all training instances or observations and is given its target value. The target value is nothing but the label of the class. Okay. So these kind of classifiers are known as lazy learners. The name lazy represents the kind of delaying of training or delaying in the processing until a new instance is required to be classified. So these methods are sometimes referred to as lazy learning methods because they delay processing until a new instance must be classified. So the target function is not estimated once for the entire input space. The target label or class of the new instance is computed locally or differently when it comes. So we will have a graphical representation of the instances and the test instance, and we will see what this algorithm is doing with the data. Right, so you have understood what it means by lazy. The instance-based methods keep using the training data from its memory without learning any knowledge from the data, right? So it doesn't learn from the knowledge. It keeps using the raw knowledge which is available to it in the form of the observations, which we are calling as training data. So every new instance requires the entire training data to be processed, due to which classification is delayed, and it is called the lazy learning. Okay. So what does it do? We have these two methods. We will be talking about k nearest neighbor learning and locally weighted regression. You've already seen that whenever we have an instance or an observation, we represent these observations for classification problem in the form of the pair of x and y data. I'll just change the ink color. So we represent the training data in the form of x and y pair, where x is itself a feature vector comprising of many such values of the corresponding attributes that we are using to describe this particular object whose class is labeled as Y. Okay, so that is what is the classification problem. When we have these values, we represent them as points in the n-dimensional space. We can say that R is a n-dimensional space. Then the nearest neighbors in this classifier are defined in terms of the distance metric. I am taking here Euclidean distance. You can also take different other kinds of metrics like Manhattan distance, or several other metrics exist for computing the distance. So let an arbitrary instance x be described by the feature vector a1x, a2x, anx, etc., where arx is the value of the rth attribute of instance x. So a1, a2, a3, etc. are describing their values. Of course, they are representing different properties of the object x. Right? I gave you one example of fruit recognition system. So A1 could be the color of the surface, A2 could be the texture of the surface, AN could be the shape of the fruit, and so on. And each different object, each different fruit may have different such values. And we will actually have only very limited number of such attributes in order to save the computational complexity from going higher. So we always want less number of attributes to define completely objects in the most discriminative way, right? So we have this distance measure. We call it Euclidean distance, in which we are trying to sum up the square of the differences of the corresponding feature values of the two instances xi and xj. The target function in nearest neighbor learning may be either discrete valued function or real valued function. So these could be either real numbered values, or these could be the labels. So we are looking at this figure. Okay. So shall I take some questions from you if you have? So the target function, it is the class here. The target function is nothing but the target label of the class. I can take here the color as representing one of these classes. Red color is representing one class, and yellow color is representing another class. So in the two-dimensional space, I am having on one axis one feature, right? So I can say it is a1x, and on the other axis it is a2x, where x is nothing but the object. Yeah, so k nearest neighbor you can use for predicting missing values in a training set. That we are not targeting this time. That is a different application. Here we are targeting the classification. Okay. And what is k? We will come to that. So consider here the following two-dimensional points belonging to two different classes represented as two different colors. Okay, the points are representing training instances by the corresponding feature vectors. I can say that there were nine objects in the fruit recognition system which were actually being used for training, right? So training means we have a supervision of what are its qualities, what are its attributes, and what is its class, what fruit, which fruit it is. So I may have its information about the color, I may have the information about its texture, and I know what this fruit is. That is where the supervision exists. So suppose in these red 9 points, I can say these were some apples, and these different 9 points in yellow color were different fruit, let us say orange. So because they owe different properties, they have different texture, they have different colors. So if I am taking these two different properties on two different axes, these objects are likely to fall apart from the objects of other class. Of course, they are likely to cluster together to the class, to the objects of the similar properties. That is why you can see that yellow points have gathered almost together, but they are not exactly um, pointing at the same point. They are not superimposed on each other, because we may have a slight difference in the texture of the orange. Even for all different objects, all different oranges, the texture estimation may be slightly different. That is why they are slightly falling apart from each other, but still finding proximity to each other because of the similarity to their own properties and because of dissimilarity from the properties of the other object. This kind of representation is known as input space, and for the visualization purpose we are taking only two features into account. We are not going for large number of features, so that we can visualize them on 2D. At the most you could take 3 different features, and you could have used some kind of projection mechanism to view the 3D data on your 2D screen. So it doesn't matter, we are taking only 2 features, one on one axis and the other on the other axis. So I can still write it like this, that this one is feature 1 and the other one is representing feature 2. So I hope that you have understood the plotting of these points. Of course, in most of the classifiers we do not need physically to point the point of to plot the points on the input space. We just use these kinds of plottings to understand what algorithm we are using. We could have used 10 different features to describe an object, and 10 different features means I could have drawn these points, I could have plotted these points in 10-dimensional space, but still humans have limitations that we cannot visualize beyond 3 dimensions. So I do not want to complicate here the understanding of the algorithm, so we are having the 2D plot. So the feature vector is in xy coordinate pair for each point, okay, right? So now there comes a test feature vector. There is an object which machine doesn't know whether it is apple or orange. It tries to just place it in the coordinate system so that its x1 and f1 and f2 points are seen, and they are and in this point particularly finds its place in the coordinate 2D plane. What to do now? Whether it should be an apple, whether it should be an orange. I am taking oranges as yellow circles and the apples as red circles, for example. So then somebody may say that because it is much closer to one of the points in red colored class, I can assign it a label as apple, which may be correct. But in actual, suppose we have certain objects which we are using to validate our algorithm, we may know that this particular object is a orange. I can say that the understanding of ours to assign it to the apple class is wrong. Okay, let us see how we proceed. It is actually a matter of assigning it a label, whether it is on the basis of a partition which we call as decision boundary, or it is a label assignment using certain other techniques. Here we are having a different technique which is known as non-parametric technique. Here we have this k nearest neighbor algorithm. This requires k to be defined as a value. So any programmer must take k as a specification to the algorithm. So if I am taking k as 3, this means that we are going to compute the distances of the nearest 3 points. So you can identify that these nearest 3 points are the ones which are closest to this blue point, and humans have this capability to just identify from the graphical data. Of course, from the numeric data of 18 points, it would have been much difficult for every one of us to identify which are the closest point to this blue point. So graphically it is quite possible But for a machine, graphics is not that required, but it has to have a way to compute its proximity to those 3 points. And whichever 3 points, right, belonging to one class are larger in number, we assign that label. So let us go ahead and see that if these 3 points which are marked as double circle, right, with the double line as a border of the circle, so these three are the nearest. Even if we compute Euclidean distance, these three will be appearing to be the nearest one to the blue point. Here, blue point is the test data. Now, since 2 points from the yellow class are nearest out of 3, we will assign it the class as orange. This is what is the crux of this k nearest neighbor algorithm. The algorithm is pretty straightforward. Here we try to find out the minimum distance of the test data from all these points. So, what will be the time complexity of finding these three closest points? Yes. So it is a nice question how you can verify whether k should be 1 or 2 or 3. K is the number of neighbors you are trying to take up into consideration for assigning a label. K does not mean the number of iterations. Iteration is only one. Here we are not going to optimize anything. So what you are trying to see here is the distances. So what will be the first thing that you will do in order to find the class label for the test data? You already have the training data where 9 points have their own values in terms of x1 and x2 or f1 and f2, and they have the corresponding class label. Similarly, you have the yellow points. They have their own position in the two-dimensional space of input, and you also know their classes. So neighbors are anyway available with us. They are actually forming the training set. So neighbors are there. But how do we compute? What I have marked as double circle, it needs to be computed by the machine. Right? I will come to the question on how to decide the value of k, whether it should be 3 or it should be 2, and what will be the effect of varying this number. Now you have to think about the process where you will be able to find the 3 different points which are the closest to this blue point. What will you do? Anyone? You will have all the instances right from numbered 1 to 18th, and then you start computing their Euclidean distances from the blue point and keep checking which first 3 are the nearest. In a way, you are trying to sort the distances and then trying to find the nearest 3 points. Once you have done this, you can assign the label according to what is belonging to class, and accordingly the label. So what will be the time complexity? The time complexity will be proportional to the total training size, because you are anyway going to compute the distances. Of course, distances computation is only once. Let us say C is the time to do the computation of the distance, and then you multiply it by the number of training points irrespective of their classes. So number of training points, that much you are going to find out. And later on, if you are taking k as 3, so out of 3 it is quite linear to find out how many of them are belonging to a class in large number. Okay, so the complexity is simple order n, where n is the training size. As training size increases, the computation increases linearly. But what about the sorting time? The sorting time will be more. Do you know any sorting algorithm? Yeah. So mud sort, you have n log n. A quick sort, you have n log n. Then insertion sort. Anybody can tell? What is the time complexity of insertion sort? N square, right? Good. So n square is the time complexity of insertion sort. What about other sorting mechanisms? Say bucket sort. Can you do bucket sorting here? No? You cannot do bucket sorting because you do not know the ranges of the distances. So bucket sorting could have been even order n, but then it could have been much difficult to know the ranges of the distances. However, this was a slight review of what you did in your previous courses, and you have a good idea of complexities. So when you proceed ahead, right, so here you have this space which we are representing as Rn. R is the real number and n is representing the n-dimensional space, right? Earlier we were taking only two dimensions as f1 and f2, so we were actually talking about a R square space, right? So it is actually the real number which you are having on each axis, and R square means it is a two-dimensional space from which we are moving to V, where V is nothing but a label of the class. So that is what I have tried to project here. It is a function from Rn space to V, where V equals the set of these values V1, V2, Vs, etc. It is a set of class labels, and Rn is the n-dimensional space. So value fxq represents the class label to which the testing sample xq belongs, right? So what does it mean? Suppose I am saying that v2 equals f of x2 or xq. What does it mean? xq is the point which is represented in a n-dimensional space. So when you apply a function, it is giving you a value. Suppose this value is v2, then we say that xq is belonging to the class whose label is v2. Okay. So just take it as a idea that classification is viewed as a mapping in machine learning. It is a mapping from n-dimensional space to the single dimensional space of class labels. Okay, basically we are assigning a class label. So now if you have delta AB, let us say we define a function delta. So if A is same as B, then this delta function is going to be 1. Otherwise it is going to be 0. Right? So I can always say that I am assuming that the class of one particular test instance is, let us say, 2, and its actual class is 1. So if I am taking 2 and 1 as A and B, then delta of 2, 1 is actually going to be 0. Basically these A and B variables are representing the actual classes and the predicted classes. Let us take it a little different way. If I am writing delta V comma f of xi, f of xi is just some class label which we are either assuming or we are predicting, then this gets a value 1 if the class of training data xi is V, right? Actual class is V, then this value will contribute to the classification, otherwise it will not. So then we are trying to find out these sums. You can look at this particular term, which is summation of all these data values over I. I is ranging from 1 to k. K is nothing but all those values. So you can always say that k, small k is less than or equal to capital K, which we were actually using this k as the number for k nearest neighbor. So this is equal to capital K, and small k is greater than or equal to 1. Okay, so basically I am rolling over all these points from 1 to k such that whichever v gives us the maximum value, we will assign that class to xq. So what are we doing here? What does it mean by argmax? It says that you have to give the argument, right? Argument is nothing but some kind of index of v, right? Where v is actually belonging to the set capital V. Capital V, I can say, is the set of class labels. I can say it has class labels as V1, V2, V3, etc. Whichever class label corresponds to the maximum value of summation delta V fxi, that gives us the class label, actual class label to xq. It is nothing but a similar thing which we were talking about. If you look at this graphical picture, here you have these 3 circles, right, within the neighborhood of blue point. If I'm taking k to be 3, so I'm taking capital K as 3. Okay. Now small k is ranging from 1 to 3. 1, 2 and 3. So small k is this. I'm trying to explain that mathematical expression in terms of the graphics. Right? Yeah, I will come to that. Why this summation is important? The summation is important because the points which are not contributing are actually contributing to the sum as 0. So let us see what happens if I'm taking, and there are 2 classes. So let me take these variables or the class labels as V1 and V2, where V1 is actually the class label of red and V2 is actually the class label of yellow. It is the yellow class label. Fine. So keep in mind that mathematical expression, I was giving you an expression as summation of those delta values. So now if I'm having V as V1, let me try to find the summation for V equals V1. Then we will see what we are getting. So that summation, let me mark as S. Okay, so S1 I will mark as the summation because I don't have the summation symbol here in the online board here. So I'm just taking S1 to be the summation of all those data values. I will show you what we were doing here. So can you keep a note on your notebook? Argmax summation delta. So I am on slide number 13. Delta V comma fx1. fx1 is nothing but the label. As I told you that f is representing the classification, and when it is applied on the input data x1, it is showing us the label. Right? V is that particular instance, that particular class label for which you are iterating over all such things and then trying to find the maximum. The V that corresponds to the maximum is going to be the class of fxq. Okay. Have you noted it down? Now I'm going back to that previous slide where I was explaining to you what will be this S1. S1 is actually the sum. So sum is ranging on the values of what? Is it on the values of k or on the values of v? Summation is ranging on the values of k. We had taken in our example capital K as 3. That means I is ranging from 1 to 3 through 2. Okay. So this sum will have 3 terms. One corresponding to I equals 1, another corresponding to I equals 2, the third corresponding to I equals 3. Right? So f of x1. What is this x1? X1 is not xq. X1 is not the testing data. X2 is not the testing data. X3 is not the testing data. Yes, so I will come to this k equals 3 question a little later. Let me tell you how we are compiling, how we are classifying, and please remind me if I am missing this point, how to decide k equals 3. So how you are going to say that fxq is going to be the red class, or how you are going to say that this is going to be the yellow class. So I'm asking you to focus on this summation. This summation is ranging from 1 to 3 because I'm taking capital K as 3. That means this summation will have 3 terms: delta V fx1, delta V fx2, delta V fx3, where x1, x2 and x3 are those points, those 3 points which are nearest to the test data. So let me say that these 3 points are actually the red one, yellow, and the second yellow. So trying to write here the sum, we should have those 3 terms. So that means if I'm having what is it? Delta. So let me use some pencil for delta, right? So I will have this delta, and what is it going to have for me? It is V1, which is nothing but red. So why not we write V1 equals red. This is one value, and f of x1, where x1 is what? Maybe I can take x1 as this point. So I will show you. So let me take this first red point, which is near the data, is my x1. So I'm trying to label these points. This is x1. Then I'm taking the second point, which is the yellow point. Okay, this is the yellow point, and I'm marking it as x2. Okay. Similarly, I'm marking the second yellow point nearest to the test data as x3, right? So with this, what am I going to get? It is S1 is equal to delta V1 equals red fx1 plus, okay. So then this will be something like delta, sorry. So please have patience, it is just taking some time so that I can explain to you why that mathematical function is representing the simple logic that we are getting very quickly through the figure. You can understand that there are 2 points which are yellow, and there is 1 point which is red, and these 3 are the points which are closest to the test data we have marked as blue. So we will assign this blue test data point as the class with label yellow. This is the simple logic, and this has been represented mathematically there using the summation of delta V fxi. So that is what I am trying to show you, the computation. So I am again taking this delta, okay, and then there will be another delta. So I am marking it here for this plus, okay, and then you will have V1 equals red and f of x1, f of x2, and this delta function gets closed. Then the third term in this sum is v1. I'm only trying to find out this entire sum for v equals v1, right? This and then this is actually v1 is equal to red, and then you have f of x2. So f of x3. So what is f of x1? It is red. You know this, right? So f of x1 is nothing but its class label. And what is this label? It is nothing but red. What is f of x2? F of x2 is nothing but the yellow class label, right? And f of x3 is nothing but yellow class label. So you have already seen the delta function. It actually gives a 0 when v1 and fxi are different. If let us say in this particular sum of S1, if we have delta v1 equal to red and fx1, these two are same, so it will contribute to 1. So I will write here equal to 1 on top of this. And the second term in this sum for S1, because v1 is red but f of x2 is yellow, these two are different. The delta function is going to give us a 0. So this is contributing to a 0. And the third term is also contributing to a 0 because of the dissimilarity of the first argument of delta and the second argument of the delta. So then this also gives a 0. So basically this S1 comes out to be S1 is equal to 1, right? And this is nothing but we wanted to find out the number of those points belonging to the class 1 within this K, which are the nearest. Similarly, if you will go on computing S2 over V2, where V2 is nothing but yellow, what will you find? Because f of x2 is yellow and v2 is yellow, the second term for s2 will give us 1. The third term will also give us 1. So basically s2 will be 2, right? So in that case, basically we are trying to find out maximum of s1 and s2. Okay. So this is going to give us 2. And what it means by arg is the index of the S which contributed to this large number. So arg of max, okay, I must write it on the upper right corner. Arg of max of S1, right, and S2, it is equal to 2. Right. So basically the second class which we are representing by yellow is the one which should be assigned to this test class. Right. So I must show you the algorithm again. Here you had seen on slide 13, it is given arg max summation delta v fxi. So what we are understanding through human logic, we need to tell the machine through this mathematical logic. What we think differently has to be communicated well to the system. And through this kind of summation, it will understand that it has to count on the number of points which are closest from the test data and are belonging to a particular class. Larger the number of those nearest points belonging to a particular class, the more is the chance to get assigned this class. So, why should we have max in this formula? I'll show you why it should be. When you're looking at this slide 11 figure, you're finding there are 2 points which are yellow, and within the range of these 3 points, because we took capital K as 3, I'm willing to find out the larger number of points belonging to a class within this closest proximity to the test data. The test data is this blue point. Humanly, we are actually finding out the proximities very fast to this small data. 2 yellow points are closest. Okay. Two yellow points are closest to blue point, and one red point is closest to this blue point. So anyway, there is a concept of maximum that we are applying. 2 versus 1. We know that 2 points, when they are closest to this test data, I will have more confidence that this particular test data is going to be of yellow class. So for S3, no, S3 doesn't exist there because we are only having 2 classes. You can see that this summation is rolling over V, all values of V, where capital V is I will show you on slide 12, capital V is the collection of those class labels. Whatever is the number of classes, that will be the size of V. So there doesn't exist anything like S3. For k equal to 3, we had taken the sum over these 3 values. Okay, f of x1, f of x2, f of x3. That is where these 3 values were rolling. Okay, so yes, so if there is another red point which is closer to this blue point, then there is a tie. So now I must come to the query regarding why we should select k equals 3 or why we should not have k equals 4. Let us take this example, which is talking about only one nearest neighbor. Whichever is the one closest point, we will assign that class to it. The concept is quite simple. Now we go to another combination. 3 nearest neighbor, we have already seen, we assigned yellow. 4 nearest neighbor will have 2 yellow and 2 red nearest points. There will be confusion. And when we have 5 nearest points, then we will assign the class label as red. So should the properties of the test data be so unstable that we are sometimes assigning it to the class 1 and sometimes we are assigning it to the class 2, just depending upon our choice of k, that may not be fair. We should have a proper way to assign this particular test data to a particular class, for which we have another strategy which is known as distance weighted nearest neighbor algorithm. So here the contribution of the k neighbors is weighted according to their respective distance from the given test data points. As we saw in the previous example where I have taken 5 NN, you can see that there are these 5 points which I have marked as green being very close to the blue point. So even though there are 2 different points belonging to yellow class, right? But their overall distance is not far away as compared to the total sum of the distances of the 3 points in the red class. So we are giving a weightage to the proximity in terms of its distance. If the distance is large, but even then there are 3 points falling closest to this blue point, we will not give a importance. Let us see how we are calculating. This algorithm is known as non-parametric algorithm because here we are not having any concept of slope or intercept. Those kind of parameters we are not computing. Okay, so the distances are not set, they are calculated. So the contribution is according to the respective distances from the given test data point. So more weight is given to the training data of the k nearest points being the closest, while the points at farther distance are given less weight. Let us look at this. So I am on slide 17. Here these are the points which are away. You can see that there are these 3 points belonging to red class, which are there in the 5 neighborhood nearest neighbor problem, and there are 2 yellow points. So we are defining the weight for each point to be considered for the class assignment using this inverse relation with the distance. So d of xi xj square is taken as the weight. Its inverse is taken as the weight. So now again we are defining the similar thing, but instead of just having delta v fxi as we were having earlier, we are also computing this entire thing with the multiple of w. So this delta v fxi is going to be either 1 or 0, but this will be multiplied with the weight, and weight is nothing but the expression which is inversely proportional to the square of distance between xi and xq. Xi is the point within the vicinity of those 5 neighbors or k neighbors, and then we are trying to figure out their contribution and then trying to compute the maximum. Now the maximum will be computed on the basis of this weight. Let us see a small computation. I am giving you some values because graphically you may not get any idea about the distances. So let the distances of the training instances of class 1 be 4, 6 and 2. You can always say that these red points are at distance 4, 6 and 2, okay, from the blue point. And let us say the distances of these 2 yellow points are 2 and 3 from the test instance. Now we are going to compute their weights. Weights are nothing but the inverse relationship with the square of distances. So 1 by 4 square is the weight of the first point. 1 by 6 square is the weight of second point. 1 by 2 square is the weight of third point. So since I am taking the class V equals V1, which is nothing but red, in the similar computation that we did in the previous example, these 3 points are going to contribute to 1 corresponding to V equals red. So their values contributed as 1 will be multiplied by their weights. That means what you are going to do is you are going to find out the sum of 1 by 4 square plus 1 by 6 square plus 1 by 2 square plus 0 plus 0. Because of delta values contribution of the other class data, right? We saw it there. So this is 0.3402, but if you will compute this for the class 2, you will get its value as 0.36, which is more. That indicates that we assign class 2 to the test sample, even though it is less in number. But because they are more close to the test data as compared to the 3 points weighted distances, 3 points weighted distances are more and these 2 yellow points weighted distances are less, then we assign this yellow point to the blue point. Blue is the test data, yellow and red are the training data. Is this clear, or you need any further explanation on this? Anybody? How we are assigning a label to the test data. So what have you not understood? Is there any specific thing, or you want the entire technique to be repeated? Can you specify what you have not understood? So how you would select this k? K cannot be all the points, right? If k are all the points, then this algorithm will be even much more computationally high. Okay, and k should not be 1 because it will be more biased towards only one outlier, which could be somehow falling very near to the test data. So we have in machine learning a mechanism to explore the evaluation of those algorithms, whether k should be 1 or 2 or 3 or 4 or even larger number. We try to estimate the accuracies of the validation data, and you will find certain trends with your test data and with your training data about the value of k. We will talk about these evaluation methods later on, and they, based on the trends, they can give you that, yeah, k equals 5 is sufficient or k equals 7 is sufficient. It is all experimental based on the data. No machine learning algorithm is fully, you know, you can say 100% accurate. It would not be. But if you try to visualize this kind of graph, I can show you how it could be. If on x-axis you take the values of k, you can take k equals 1, k equals 2 and so on. And then you can take on the y-axis the accuracies, okay, accuracy of classification. You may get certain thing. You may get certain thing like this: when k is increasing, k accuracy is increasing, but after a certain point of time, the accuracy doesn't show much improvement. In that case, we pick up experimentally decided or investigated value of k. So this is based on the underlying complexity of the data, how you would be picking up this value of k. You will experiment with all values of k equals 1, 2, 3, 4, at least till n by 2 or so, and then you will find a trend. These kind of graphical representations are essential because we want to find out the trend of the behavior of algorithm. This is very essential in machine learning. So there was a question regarding class 2 performance, right? So why this class 2 is assigned to the test sample? Because its distances in totality are lesser. 1 by 2 square plus 1 by 3 square is coming out to be 0.25 and 0.1111, which is summing to 0.3611. So let me take some questions from Naveen. Yeah, when it is class 1, according to diagram, it is yellow dot. Why? No, I'm not getting why when it is this diagram, why should you say it is yellow? Okay, based on k equals 1, you're saying? Because 2 is minimum, so 2 is here also, and 2 is also for red class also. There is one point which is at distance 2 from red class, and there is one point which is at distance 2 from the yellow class also. So instead of having this kind of confusion, if you are going for a 5 nearest neighbor classification, you will get it like this. Okay. So diagram distances may not be that much easily, taken correctly. So you go with the values which I am giving you here. So input to the class 2 is its distances. I mean the class 2's, those points which are nearest to the test data, their inverse distances or the inverses of the square distances. That is the criteria for class 2. And that is how we are getting this value 0.3611. By multiplying 1 by 4 to 1 and 1 by 3 to 1 for the contribution of these two yellow points in that particular sum. The sum is of 5 terms, of which for class 2, 3 terms are going to be contributed 0 because of the difference between the first and second argument of delta. Are you getting this point? So how to find if I place my test point at wrong place? See, there is nothing like this that we have to find whether we place the test point at the right point or not. Okay. So it is about its feature extraction. we extracted the feature of the unknown object, right? Based on its values corresponding to the attribute computation, pre-processing, we are marking it there. Wherever it falls, we don't know which class should it belong to, but then we just plotted it according to the pre-processed attribute computation. So there is no need for us to verify whether we place the test point at the wrong place or not. Okay. So any other question which I have not answered yet? Yes. So what about 0? I'm coming to this computation of delta, which I explained for non-weighted example. This one, delta V fxi. I'm now explaining why for all these values of k, the terms of delta will be contributing either 1 or 0. Why should it be? Let me show you. It is on slide 11, which I have explained here by typing certain things. You can look at this. So V1, when it is taken as red, I am iterating over these two values, V1 and V2, for the class labels. And for each class label, I am going to compute this sum of the delta values. Delta values have two arguments, right? One is about the class label, another about the class of each point of those three neighbors. If I'm having k as 3, I'm iterating this sum over these three values, fx1 plus fx2 plus fx3. So if I'm taking v1 as red, then only fx1, which is the class label of x1, I gave you this idea that x1 is that red point and x2 is that yellow point and x3 is that yellow point. So f of x1 being a red point, it is same as v1. So delta value is contributing a 1, but for fx2 being a yellow label is being compared with v1, which is the red. These two are two different things. So delta is contributing a 0 in this sum. Similarly, the third term corresponding to v1 equals red, comma fx3 is contributing a 0 because v1 is red and fx3 is yellow. These two are different. You can again look at the definition of delta. We are defining this delta function on slide 13, where I'm saying delta AB is 1 if A and B are same, otherwise it is 0. So basically it is just a way to count the number of samples within those k neighbors belonging to a particular class, and whichever class has more representation in the neighborhood of the test data, we will assign that class to this test data. Is this all right? Anish? Okay. Any other question? So weighted sum is a kind of remedy from the previous limitation where we were actually assigning erroneously large numbers in this case. Even though the 3 points out of 3 red points, 2 are very largely different and much farther from the test data, because of the numbers we were biased to assigning red as the class label to this test data. In the next class later on, of course I will be taking a break today, and after that I will give you more discussion on different other classifiers. But when later in the next class, I will show you more graphical representations using the Python scripts, so that you are working on the real data and seeing these points on your own, right? I will give you the script and then you can run it on your own after installing basic Python modules and some Anaconda modules and library of machine learning. But I do not want you to directly use the machine learning library, because then you will be more confused about the concepts. What is happening inside the functionalities also need to be known to the students, right? So class 1 I am taking here in this figure as red, and class 2 I am taking as yellow. I think I did this. How distances are calculated? So distances are calculated using the Euclidean distance metric in this. I'll show you how it is working. It is this Euclidean metric on slide 8. So the values, corresponding values of the feature attributes are subtracted from one and then taken as square, so that negative sign is nullified here and then taken the summation. It is, if you will recall your high school mathematics, you will see how you computed the distances between 2 points in the x1 and x2 plane. Is this all right? So right now I'm taking a small break, then I will come to discussion on Bayesian classifier. Okay, so naive Bayes classifier, and yeah, in the last example we had only two classes, one represented by red color and the other by yellow color. Okay, green is actually not the class. I'll show you. Green is not the class. Green is only representing on the slide 17. Green is representing the neighbors, even though their original classes are red and blue, red and orange, red and yellow, sorry. So there is no green class, fine. So distance is a measure between 2 points. The distance between 2 points, yeah, of course. If it is two-dimensional, the metric is quite straightforward, as you did in your earlier school mathematics. And if it is a more dimensional space, then this Euclidean distance formula extends to that sum. So then in that case, I'll show you, this sum will be on different dimensions. As I've mentioned here, n is the dimension. Okay. Yes, so dxi xj is calculated using the Euclidean formula. Yes. Any more questions? Fine. So I'll take a 5 to 10 minutes break, and then I will join you back to discuss Bayesian classifier. I'll come back and answer your last question. Okay.